Hello, I'm Tingyu, and I'm from P4 Group 16, and together with me is Gerald, Jovan, Nigel, Rachel, and Branson, and we'll be doing signature forgery detection for our machine learning project. So these are tables of contents. Next, for the problem statement and data collection, signature fraud, a significant financial threat involving unauthorized use of signatures, requires robust detection system to mitigate losses, leveraging datasets like SEDA to train machine learning models for accurate verification. For our data collection primary set, we uses 55 SEDA signature datasets from Kaggle, 24 genuine and forged signatures per subject, totaling to 1320 signature images. Additionally, we uses 11 real-life signatures, 24 genuine and forged signatures per subject. Next, I'll pass on to Nigel to talk about data processing. Thank you.
Thank you, Jing. Hi, I'm Nigel. Today I'll be discussing our group's methods for processing and extracting features. We begin by enhancing the image quality. This includes converting images to grayscale, applying Gaussian blur to reduce noise, using candy edge detection to emphasize edges, lastly, converting images to binary by using Otsu's thresholding. We then compare the original and processed images side by side to ensure that our pre-processing enhances key features which are necessary for accurate analysis later on. Generating signature pairs. We use the make_pair script to generate over 30,000 signature pairs, which are both genuine pairs and genuine forged pairs, to provide a comprehensive dataset in order to train our model. Our edge-based features, we use sober gradients to detect edges, capturing the stroke strength and direction. Then onto our texture-based features, we apply Gabor filters at multiple frequencies and orientations to analyze texture. And lastly, with intensity-based features, we enhance the intensity contrast with CLAHE, computing the Shannon entropy and variance to analyze intensity distribution. Now moving on to our normalization and feature analysis. We use different scalars for our features to ensure consistency. Min-max scalar for edge-based features preserves edge details. Standard scalar for texture-based features optimize texture analysis. And robust scalar for intensity-based features, which reduces the impact of outliers. From our analysis, it shows that edge-based features provide basic insights, but are limited due to overlap. Meanwhile, texture and intensity features show significant variances and are more effective at distinguishing forgeries. Our visualizations then confirm this finding, showing that texture and intensity features are vital for detecting forged signatures. That is all for my segment. I'll now pass my time to Jovan, who will talk more about model training.
Thank you, Nigel. So now we'll be talking about model training, which we use three different types of machine learning models. The first being support vector machine. So for our base model, we achieve a validation accuracy of 84.12%, with our forged signatures achieving a precision of 86% and a recall of 82%, meaning that some forgeries are missed. And for our genuine signatures, we achieve a precision rating of 83% with a recall of 86%. So it also shows that some genuine signatures are falsely flagged. So for our hyperparameters tuning, we tuned our parameters with C, gamma, and kernel. And we use the best parameters of a C to 100 gamma scale, kernel RBF to get a best validation accuracy of 99.51%. So for our scalar selection and feature selection, we use mutual information to identify and select top 35 most relevant features for classification. And then we retrain our model using the best parameters and 4 different types of scalars, the best being robust scalar, achieving validation accuracy of 99.67%. For our model training on random forest, for our base model we achieve a validation accuracy of 99.74%. With our forged signatures, we achieve both precision and recall of 100% with no forgeries missed. With our genuine signatures, we achieve both precision and recall with 100% as well, with no genuine signatures falsely flagged. For our hyperparameters, we tune parameters with criterion equals to entropy, max depth equals to none, minimum samples leaf equals to 1, minimum sample split equals to 2, and n estimators equals to 300. And then we use these best parameters to achieve the best validation accuracy of 99.82%. For our scalar selection and feature selection, we use the same mutual information to identify and select the top 35 most relevant features for classification, and then we retrain the model using the best parameters and 4 different types of scalars, the best being max app scalars, achieving validation accuracy of 99.95%. Now I'll pass on my time to Gerald.
Thank you, Jovan. Now I'll be moving on to model training on XGBoost. The base model achieved a validation accuracy of 99.92%, and the classification report shows that the forged signatures have both 100% precision and recall, which means that there were no forgeries missed, and for the genuine signatures, they have a precision of 99.9% and a recall of 100%, which means that there are very few false positives. After this, we went to use grid search to get the best parameters of co-samples by tree of 0.7, learning rate of 0.2, max depth of 5, and estimators of 300 and subsamples of 0.7 to get the best validation accuracy of 99.91%. Lastly, for scalar selection and feature selection, we use mutual information to select the top 35 most relevant features and then retrain the model using the best parameters and the 4 different types of scalars. The best of the scalars was MaxApp scalar, which achieved a validation accuracy of 99.91%. Next, on the evaluation of tuned models on our test data, the goal of this is to evaluate the performance on our trained models XGBoost, SVM, and Random Forest on real-world signature samples that were collected from 11 individuals, which is 20% of the total dataset. Those individuals also contributed 24 genuine and 24 forged signatures each. On to our findings is that SVM generalized best achieved the highest real test accuracy of 52.03%, indicating that it has better adaptation to new handwriting styles. XGBoost and Random Forest overfitted more, as despite their high validation accuracy, their real test accuracy dropped significantly. We are also able to tell that unseen handwriting variation had caused performance degradation, which emphasizes on the challenges of detecting skilled forgeries. Next is the evaluation on deep learning versus traditional ML, where the Siamese network achieved 100% accuracy on training and validation data. We also evaluated this Siamese model on our real test set using the same pre-processing and found out that the real test accuracy dropped to about 50%, which indicates that there is a lot of overfitting and poor generalization. Our SVM model outperformed the Siamese model with 52% accuracy on the test set, which shows that traditional ML models have better generalization, lower computational costs, and higher practicality for deployment, and suggests that they can outperform deep learning models when data is limited or computational efficiency is prioritized. Okay, thank you. Next, I'll be passing my time on to Rachel.
Thank you, Gerald. Moving on to further enhance our models, we used ResNet50 for deep feature extraction, combining CNN-rich representations with traditional machine learning classifiers. This hybrid approach improves performance and generalizability by balancing deep learning's robustness with classical efficiency. So for data preparation, we pre-process the images according to ResNet50's input requirements, and then it was used to extract the features. Lastly, signature pairs were created by combining genuine and forged samples, forming the dataset used for training the models. For training, tuning, and evaluation, we adhered to the same systematic approach as in our previous experiments, which is first to train a baseline model, then hyperparameter optimization using random search, scalar selection, and lastly evaluate on the final model for each algorithm. Looking at the model performance shown in the image, we observed that SVM achieved the highest validation accuracy. However, this came at the expense of extremely high computational cost, both in testing time and model size. To further validate our findings, we evaluated these tuned models on our real-world test dataset. And from the results, SVM achieved the highest test accuracy but at a significant cost. XGBoost, on the other hand, provided the best trade-off, balancing test accuracy of 67.18% with significantly lower computational overhead, making it the most practical model for deployment. Thus, based on the balance of accuracy, speed, and efficiency, we conclude that XGBoost is the best performing model for real-world signature verification.
In conclusion, our team demonstrated the potential of machine learning and deep learning techniques for signature forgery detection. We explored three machine learning models: support vector machine SVM, random forest, and XGBoost. These models were trained using a combination of edge-based, texture-based, and intensity-based features, with SVM achieving the highest test accuracy of 52.03%. We proceeded to introduce ResNet50 for deep feature extraction. This transition from traditional handcrafted features significantly improved our model performance, with XGBoost achieving 67.18% on real-world test data, emerging as the best performing model. XGBoost provided a good balance between accuracy and computational efficiency. We were able to capture more complex and subtle patterns in signature images, making it suitable for real-world deployment. All in all, our project highlights the potential of using deep learning to improve forensic document analysis, thereby enhancing the security and reliability of signature verification systems.